Okay. I want to play this. Okay, good. All right, how's everybody doing? Doing okay? Yeah. Um, do we know exactly what day our exams on? Did we ever discuss this?
I forget. It was on May 9th at 8 a.m.
Oh, God, no, we're not doing that. May 9th is what?
It's
Wednesday?
Monday, I think.
Okay, it's a Monday. So, is there a dead? There's not. Is there a dead week, or classes go all the way up until Friday?
I think they go.
Okay.
May 5th is my last day in anthropology, but I don't know
Yeah.
if it goes farther for other classes.
Okay. Well, let me. I'll sit down and figure it out, and I'll send out an email and let you guys know. I think I know there's at least one homework assignment put out there, and I think there's actually two, but the second one is really short. It has to do with some of the stuff we're going to start to learn about now, but the solutions are really short, so it shouldn't take a lot of time. And like I said, you can, give it to me the day before grades are due, which I don't know the date, but I'll put it in the email that I'll send out to everybody. Okay, so you'll have plenty of time to work on it. Okay, so today we're going to start discussing our last topic of quantum mechanics. You can see everybody tearing up, getting nostalgic over quantum mechanics. But so what we want to do is start to talk about relativistic quantum mechanics. So this is a very interesting topic, and you would think that it would be very straightforward, but it turns out that special relativity and quantum mechanics do not like to play very well with each other. Okay, and so that forces us to kind of expand our quantum theory if we want to incorporate particles that are moving very fast, which is typically the types of experiments we're doing, right? We're shooting, if you're in particle physics or nuclear physics, you're typically shooting particles at each other at close to the speed of light, right? So you need a quantum theory that describes very fast particles. Okay. So this all started back in the beginning of the 20th century. Seems weird to say the last century, but it started in the last century, the beginning of the last century, these early years of the 20th century saw basically two of the most successful and kind of earth-shattering theories that were ever developed. And one was the quantum mechanics. One was quantum mechanics, which we all know is basically the laws of physics for the very small, right? When you're probing things at very small scales. And the other is special relativity, right? And this is a theory of how the laws of physics apply to reference frames that are moving very fast. Right? And so having these two theories that were both tested in their own respective realms, very precisely, at least as precise as they could do for that era. These theories were very successful, and so people thought, okay, well, there must be a way to join the two, right? To be able to write down a fully relativistic quantum theory. Okay. And it proves to be very difficult, and we'll see why later. And actually, it wasn't until Dirac came along in the late 20s that a self-consistent theory emerged, right? And this is a theory that Dirac developed for specifically electrons or spin 1/2 particles, which were only one of the real fundamental particles we had at the time. So that's why I was interested in describing the relativistic theory of electrons, along with the fact that you imagine that and atoms. If you think about, if you can, if you interpret electrons as spinning around the nucleus, they're going to be spinning really fast. Right? They're going to be spinning close to the speed of light. So you need some relativistic theory in order to make predictions about, or precise predictions. And Dirac was the first one to do it. It's now, Dirac's theory. There's nothing wrong with it, but it's an effective theory. Okay, so it means there's nothing very fundamental about it. He just was trying to describe, physics of very fast electrons, and he basically just took tried something out, and it worked. Okay, and it worked to describe, the dynamics of an electron, but it also made a prediction of the positron, which is the antimatter particle of the electron. And that was, people didn't believe it, for years, and then a few years later, I think 3 or 4 years later, somebody actually discovered and observed the positron, right? And so it gave credence to Dirac's theory, but we'll see that Dirac's theory has a lot of ugly warts and things, that theorists don't like. Okay, so we're going to take a first stab at this, all right? What we want to do, our main goal is to come up with a relativistic quantum mechanical theory, right? And if we're doing this, we have to make sure that we're imposing the rules of both special relativity and quantum mechanics, right? And so the main rules that we want to focus on are in special relativity. We all know that the laws of physics are identical in inertial reference frames, right? So if I have a reference frame that's moving, at some constant velocity with respect to another reference frame, the laws of physics have to be the same, right? And that is kind of related, or another rule, if you will, of special relativity is that you have to treat space and time democratically. And what I mean by that is that you have to put them on equal footing, right? So that was one of the first things that Einstein did, was to say, okay, let's put space and time on equal footing. He he treated time as almost another dimension, really, right? And the rules for quantum mechanics that we have to make sure we obey is that the typical ones that each state that we're concerned with is described by a wave function, right? And that wave function contains all the information that we can ask, right? What's the momentum? What's the spin? What's the particles? Favorite flavor of ice cream? Whatever. All that information is contained in the wave function, right? And the wave function itself is not observable, but we use it as a tool in order to construct probabilities, right? Probabilities for things to happen. And so what we want to make sure is that we can write down a wave function, and we can interpret this thing modulus squared as a probability to find a system in a particular state, right? So the idea of this being a probabilistic theory is, it's a key, it's a key feature in quantum mechanics, right? And we've discussed all that last semester. Here are some other rules that we have to obey. Quantum mechanics is full of rules, right? So if we want physical observables, we've seen that we have to represent those with linear Hermitian operators, right? And if an operator is Hermitian, then we say that its eigenvalues have to be real, right? We prove that. We prove that its eigenstates of this operator are orthogonal, right? If it's Hermitian, and in general, it'll satisfy some eigenvalue equation where this wave function is an eigenfunction of some operator capital omega, and when we operate on the wave function, it gives us some eigenvalue, and that eigenvalue has to be real if we want omega to be an observable. Okay, so the other things we can do, or that we do in quantum mechanics, is we can always kind of deconstruct a general wave function in terms of an orthonormal set of eigenfunctions, right? And we're always free to choose what basis we use. Typically, if we can, if we're dealing with a Hamiltonian, and the Hamiltonian, is commutes with this guy, right, then we find it advantageous to choose the eigenbasis of omega as our eigenbasis of the Hamiltonian. Right? And so in general, we can always decompose a general wave function in terms of eigenfunctions of some operator times some coefficients, and those coefficients are like the projection of our original operator along some particular axis. Right? But the role that these coefficients play is that when we take modulus squared, these guys squared give us the probability that we'll measure some eigenvalue omega n. Right? So we've seen that when we take expectation value of some operator, we can basically write it down as a linear sum of these probabilities times the corresponding eigenvalue. Right, and then finally, the last rule is that the time dependence or time development of our system is expressed by the time-dependent Schrodinger equation, which says that the time derivative of the wave function up to some constants has to equal the product or the result of the Hamiltonian operating on our wave function. Okay, and the Hamiltonian, which corresponds to energy, which is an observable, so that tells us that the Hamiltonian itself has to be a linear and Hermitian operator. Okay, all right, so having laid out those rules, which you should hopefully know by heart, let's try to construct a relativistic quantum theory. Okay, and we're going to start with the simplest case, which would be a free particle. Okay, so just to remind you, in a non-relativistic theory, the Hamiltonian is just basically p squared over 2m, right, the kinetic energy. And if we promote p to an operator and work in the position basis, then we pick up the factor of h bar squared del squared. Right? And if we plug that into the Schrodinger equation, we get this. Okay, so this is the normal time-dependent Schrodinger equation for a free particle. Right? We all know how to solve that, hopefully. Right? But automatically, you see that if you try to extend this to a relativistic theory, right, where the particle is moving very fast, you can automatically see that you're violating one of the rules of special relativity, right? And that rule is that we have to treat time and space on an equal footing, right? In a mathematical sense, that means that whatever the power of t is, the spatial part should come in at the same power, right? And that's not the case, right? Here we have second order derivatives in space, and on the left-hand side, we have a first-order derivative in time, okay? So right off the bat, it looks like, and we didn't do anything wrong in quantum mechanics. This is the way we would write it down. But we see now if we tried to extend this, if we tried to take p all the way up to the speed of light, and in the relativistic realm, then we might have some problems, okay? But I'm going to forget about that problem for now. We'll come back to it later. Okay, so let's say we want to consider a fully relativistic particle. Okay, so Einstein told us that if you're talking about a fully relativistic particle, the momentum, the energy, is not going to just be p squared over 2m, right? You have to account for the in the more general way, you have to account for the rest mass of the particle, right? So the dispersion relation, or the relation between energy and momentum, becomes this thing, right? So that's the energy, right? That's the classical energy. But if we want to promote this to an operator, the mass is a constant, c is a constant, right? So all we have to do is, like we did before, is promote this momentum operator to be this momentum factor of momentum to be an operator, right? We promote this to be the momentum operator, and if we do that, we get a quantum mechanical operator that looks like this. Okay, and you say, okay, that's no big deal, right? But think about it. We've never encountered an operator like this that is inside of a square root, right? And that square root was the main kind of roadblock for theorists, who were trying to put these two theories together. They didn't know how to deal with it, right? And you can see that when you put it in the Schrodinger equation, it looks even nastier, right? So I've still got first order time over here, and now I've got a square root, and you say, well, that square root might make this linear, but it's not necessarily the case, right? And in fact, one way that people try to work with this is to use a Taylor expansion, right? So typically that's what you would try to do if you had an operator under a square root or operator being raised to some weird factor. You try to work with a Taylor expansion. The problem is that when you do the Taylor expansion, there's nothing. We're expanding it. We're doing a Taylor expansion to all orders, right? And we can't really cut off any parts of it. It's not like perturbation theory where you cut off the small parts, because they're all going to contribute basically in an equivalent way. And so what you end up with is time of the first order on the left-hand side, and on the right-hand side you end up with spatial dependence that starts at quadratic, starts with space squared, right? And it actually starts at a constant, but that constant doesn't do anything. But then the spatial dependence starts at squared and it goes all the way up. So it considers all powers of this del, right? And that turns out, for reasons that I don't want to get into, but maybe you've seen, if you've been through E&M, hopefully you talked about special relativity. And the problem is that if you have all powers of del, you can show that this theory is non-local. And non-local is a bad thing. Right? It's a bad thing because it basically tells you that you can throw causality out the window, right? Okay. Okay. All right. So we have this situation now. We have got this equation, the relativistic Schrodinger equation, and we don't know how to deal with it. Okay. One thing we could do is just try to get rid of the square root, right? By considering not h operating on psi, but h squared. So operating twice with the Hamiltonian, right? That would do away with the square root, right? So the h squared would be in momentum space, it would look like this, or in position space, it would look like this, right? And so what you can do is try to iterate the Schrodinger equation. In other words, you take IH bar d by dt on psi, h psi, and then do it again, right? So on the left-hand side, you'd end up with minus h bar squared, del squared t squared, and on the right-hand side, you'd end up with this stuff, right, operating on psi. Okay, so then you say, okay, if I do that, it looks like I might be in good shape, right? So I end up with this thing over here, which is second order in time. And over here, my spatial dependence is second order, okay? So it looks like we're doing okay as far as special relativity goes, okay? But what we'll have to do is test, whether or not we're violating or screwing anything up in quantum mechanics, okay? So I meant to say here that we're using the general fact that if you have two operators that commute, so in this instance, it would be our Hamiltonian and the time evolution operator or the time derivative. If those two commute, and you know that these two operators satisfy this operator equation or this equation where b psi equals or a psi equals b psi, the fact that they commute tells you that you can do this iteration. Right? So you can write down the equation where a squared operating on psi equals b squared psi. So that's basically what we're doing. Oops. Okay, so you can work with this form, right? Or you can take kind of the higher road and start to introduce the special relativistic notation, right? Hopefully you guys have seen it. We'll talk more about it later, but I just wanted to show you that you can write this equation in a very compact form. So you introduce the covariant derivative, right? Which is, again, it's a four vector, right? So it has four components. The first component is like the time derivative, and the second component, or the 2, 3, and 4 components are the spatial derivatives. And you can define a contravariant vector or contravariant derivative. And if you do that, you notice that this term combined with this term is nothing but del squared, where del squared is del mu dotted into del mu. Okay? All right, everybody's get the general idea? Okay. So in the end, you can write that equation, what we would call the squared Schrodinger equation, I guess, ends up looking something like this. Right? And a lot of times if you look in a textbook, you'll just see del squared plus m squared. right? And that's because most of the time when we talk about relativistic theories or quantum field theories, we set C and H bar to 1, right? So if you set C and H bar to 1, you get a really nice equation that says del squared plus m squared operating on psi is equal to 0. And then the name of the game is to solve that equation, okay? And this equation is a very special equation. It's called the Klein-Gordon equation. It plays a major role in quantum field theory. And if you take quantum field theory, you will spend a lot of time talking about the Klein-Gordon equation. But the question is, does it make a good equation? Is it a good equation for relativistic quantum mechanical electrons? Right. So that's what we're focusing on. We're trying to solve this problem of solving a relativistic quantum theory for electrons. Right. And so the first thing we would note is that we've introduced something that's really weird. Right. By squaring H, right, we're allowing for the fact that the Hamiltonian can be plus or minus the square root, right? So we've introduced this Hamiltonian that has this weird square root out front, right? And so it looks like, to get an equation that obeys special relativity, right, we've kind of sacrificed, before we had positive definite energy, right? And now it looks like we're going to have some negative energy solutions possibly, right, because of this minus sign. Okay, and so people started asking, well, if we haven't done anything wrong, is there a physical interpretation of this minus sign, right? And we'll get to that later. The answer, I'll spoil it for you. The answer is yes. You can come up with a physical interpretation. It's not exactly right, but it works. Okay. Right, and so in order to derive that Klein-Gordon equation, we had to alter the Schrodinger equation. In other words, we squared it, right? And so that might be a point of concern. Did we mess something up when we squared the Schrodinger equation, right? And one way you can do this is to try to construct a continuity equation. Everybody remember what the continuity equation is in quantum mechanics? It's something like d by dt of rho, where this rho is some probability density. All right. And then there's some term, I'm going to get the factors wrong, but it's like del dot j equals 0. There's some prefactor, some h bars and crap here. But the important point is try to form a continuity equation, right? And then you would integrate, if you integrate it over all of space, use Gauss's theorem, you can show that this thing is 0, right? So you can show d by dt rho is equal to 0. And this is this was one of the major findings, when you start studying quantum mechanics. I think it's like chapter 1 of Griffiths, right? You go through this and you show that in a quantum mechanical system, this probability density is conserved, right? And that was starting from just the regular time-dependent Schrodinger equation. All right. So here we want to try to do the same thing. Okay. So we follow kind of the recipe. If you go back and look at how you got to this point, you'll see that you're doing what we're doing here, which is you first take the Klein-Gordon equation. So this guy, this piece right here, the first term. Let me do it with the cursor so you can see. So you take this term, which is the original Klein-Gordon equation. You multiply it from the left by psi star, or psi dagger if you want. And then you take the Hermitian conjugate of the Klein-Gordon equation, which would be this guy, right? So del squared, all this stuff is just real, so it just stays the same. And this becomes psi star. You multiply that equation from the left by psi, and then you take the difference between the two, okay? And what it gets you is something that looks like this. So basically these mass terms cancel out, and you end up with psi star del squared psi minus psi del squared psi star, okay? And you can actually, think about it in terms of the Schrodinger equation. These would be like first order derivatives, okay? And so what you can do is actually rewrite this thing. So you can use integration by parts, or use the what's it called, the chain rule. in reverse, right? So I rewrite this term as a total derivative minus the derivative. So I'm basically moving one of these derivatives onto the psi star, right? And then I do the same thing for this guy. So that's where this total derivative term comes in and this guy comes in, right? And what you should see is that I think I messed up a sign here. I think this should be plus, right? Yeah, this should be plus. Sorry. So this should be plus, right? And so the second and the fourth terms cancel out, and you end up with a total derivative of this thing, okay? Remember, in quantum mechanics, or in non-relativistic quantum mechanics, this thing that's being that would be taken, would be the object of this derivative rho is like psi star psi. Right? That's how we interpret, or how we construct a probability density. Okay. And so now what I can do is I want to make connection with, the way we've learned for non-relativistic particles. So I can expand out those four derivatives. So I just need to, expand these back out into time and spatial derivatives. And what I end up with is something that looks like this. Okay. So this has the form of a continuity equation, right? But here we're interpreting this stuff in square brackets as our probability density, right? So it's not psi star psi anymore. It's psi star times a time derivative of psi, right? And then this stuff over here we could identify as a current, right? Probability current. But what this equation is telling us is that this probability is not conserved anymore, right? If we do the normal trick of integrating overall space and using Gauss's theorem to get rid of this term, we find that this thing, d by dt of rho, what we're calling rho, is no longer necessarily zero, right? So it seems like, so the end result is that probability is not conserved, right? And that's a bad thing in quantum mechanics. We've always, that's always been our, I don't want to say it, we always want to try not to screw that up. Right. Anytime we talked about time evolution operators or spatial translation operators, any type of operation that we wrote down, we always wrote it in terms of a unitary matrix, right, or unitary operator, right. And the whole purpose of that was that we didn't screw up conservation of probability. Okay. And so it looks like here we've violated this conservation of probability. And so another way, to think about it is that, by raising the time dependence of the Schrodinger equation, which is what we did, right? When we went from our original Schrodinger equation, we basically square both sides, right? The operators. So we've raised the time dependence to quadratic, right? Over here, we're still at del squared, which the normal or non-relativistic Hamiltonian has. Okay. But what we've done by raising the time dependence was we've basically broken quantum mechanics in the worst possible way. Right? I can't think of a worse way to break quantum mechanics than to destroy, the whole probabilistic interpretation. Right? That's what quantum mechanics is built on. Okay. And so it turns out, and you can actually see this statement if you go back to Griffiths, chapter 1. I don't remember the page, but he says in there explicitly that the time dependence has to be linear, right? Of any equation that you write down for a quantum system, if you want to conserve probability or conserve, this probabilistic interpretation, the time dependence has to be linear. And he actually works through a proof or some, semi-proof. Okay. So we have an equation, the Klein-Gordon equation, that looks like it's it works well under a special relativity. We would say it's Lorentz invariant or it's covariant. So it has, if you do a Lorentz transformation, it would still look the same, right? So that's the laws of physics looking the same in two reference frames. But we've broken quantum mechanics in the worst possible way by doing this. Okay, so it seems like the Klein-Gordon equation is not a good candidate for a relativistic description of an electron. Okay, everybody with me on that? Okay. All right. So that's where Dirac came in. So that was the situation until Dirac started looking at this. And so, so what we've seen so far and what Dirac realized was that in order to write a fully relativistic equation, there's two things that you need, right? Or, two basic things that you need. You have to have time and space appear at the same order, right? And you also have to have time dependence, which is first order, right? So I'm no, philosopher, but putting those two together tells me that the spatial dependence has to be linear, right? So how do you make the spatial dependence be linear? Okay. And so what Dirac did was he looked at this equation, right? And he said, okay, over here I have time first order. I have to leave that part alone, right? On the right-hand side is the square root of this nasty looking thing, right? But, he said, if this thing inside of here can be written, if you could refactor it somehow to being a perfect square, right? Everybody know what I mean by perfect square? So it would be some quantity, parentheses, square, right? Then you could take the square root, right? And what you want that quantity inside the parentheses to be is linear in momentum. Okay, so Dirac said if you could figure out a way to write this stuff under the square root as a perfect square, you'd be in business, right? You'd have a theory that's linear in time, and time and space would be on the same footing, right? They'd both be linear. Okay, so how do you go about doing that, right? So in other words, what do you want to do? So let's switch back just for simplicity of notation. Let's go work in momentum space, right? So now my operator under that square root looks like this, okay? So what he's saying is that this thing has to be written in terms of a perfect square, okay? So what he wanted to do was write this in terms of a perfect square, and what he did was he introduced these new quantities, these new kind of coefficients, one for each of the spatial directions, and then one for the mass term, right? So he wrote this thing as a sum over these terms, right, squared, right? Or you can rewrite it in terms of dot products, right? So you can think of this as almost a vector. We'll see that it's not a vector, but you can write it in this shorthand notation, right? And if that's the case, if you can do that, right, then you can plug it into your relativistic Schrodinger equation. You take the square root, right? You just keep the positive root because you want positive energies, right? You think you're being safe, okay? We'll see that we're not. And we end up with this equation, right? Which is first order in time and space, okay? And this is Dirac's equation. This is the Dirac equation, okay? And it's, you can write it in a slightly simpler form using introducing relativistic notation, and we'll do that later. For now, it's easy to work with this equation. Okay, so we've kind of just guessed, right? That's saying, okay, we can write that operator, perfect square. We end up with this, but what the hell are alpha and beta, right? Basically what we can ask ourselves is not what they are, but what conditions do they have to satisfy, right, in order for that statement to be true, in order to be able to say that this is equal to that, right? And so the way you do it, basically, and I think it's one of my short homework problems, is to square it out, right? Square this stuff out, right, and make sure that it's going to equal this, right? That's going to give you the conditions or the conditions on alpha and beta, right? And there's several things that pop out. Okay, so first, we're assuming that alpha and beta are time independent, right? But we also have to assume that they're position independent, okay? So they don't depend on space, right? And that just comes, because you have to be able to pass these momentum operators through them, right? You have to pass the derivatives when we write them in position space, okay? It turns out that they can't be C numbers. Everybody know what I mean by C number? It means it's not an operator. It's just like a number like pi or 2 or 42 or whatever number you want, okay? That's what we call C numbers. So they can't be C numbers, and in fact, they have to be matrices, right? And these matrices, in order to be able to square this thing out and get back to what to this, they have to obey a very particular set of relations, right? First, they all are equal. When you square them, they give you back the identity matrix. Okay, so these conditions come from going through that exercise of expanding that out and seeing what you need in order to get the original, right? And then you find that they anti-commute, right? So this basically, when you're doing that calculation, what this does, this is killing off those cross terms, like cross terms between px and py or whatever. Okay. All right. Another condition which is not as easy to prove is that they have to be traceless. Right? They have to be traceless, and they have to have eigenvalues of plus or minus 1. Okay. And so, again, I'm no mathematician, but if they're traceless and they have eigenvalues of plus or minus 1, it's telling me that they have to be even dimensional, right? I have to have equal numbers of plus 1s and minus 1s. Okay? All right, so they have to be even dimensional. So these are the rules just by going through that calculation. And, well, 3 is kind of a different proof or a different part, but you get these identities, right? You can show that they have to be traceless and have eigenvalues plus or minus 1, which implies they have to be even dimensional. Okay, so we've got a set of rules for building these matrices. Okay, so we know we're dealing with an electron, right? Now psi is an electron, and the electron wave function we always write as a 2-component spinor. And so what we would like is for alpha and beta, or what we would need in order for this guy to be a 2-component spinor, we would need alpha and beta to be 2 by 2, right? That's the only thing that makes sense. If I write this as a column vector, right, it'd be a 2-component vector. The only way that it makes sense is if this guy is a 2 by 2, or has, has 2 as one of its indices, right? And so 2 by 2 is what we would like alpha and beta to be. Right? And so what we're looking for, if you go back and look at this, we're looking for 2 by 2 matrices that when you square them, you get the identity matrix. They anti-commute, right? They have eigenvalues of plus or minus 1. They're even dimensional. They're traceless, right? And it sounds familiar. It should sound familiar. It's the Pauli matrices, right? The Pauli matrices obey all of those conditions, right? The problem is that we actually need 4 matrices, right? If you go back and you count, right? You count, we need 3 alphas, alpha x, alpha y, alpha z, but we also need this beta. Okay, this beta is kind of what's screwing it up. Okay, so alpha x, alpha y, and alpha z, you'll see are related to you can relate them to the Pauli matrices. Beta, which is the new thing, turns out to screw it up, right? So, and you learn early on that these guys span the space, right, of a spin 1/2 representation, right? So you can't introduce another orthogonal matrix, right? So those 3 span the space. So we don't have we can't use the Pauli matrices because we don't have 4, right? So what we have to do, if we consider the fact that these guys have to be even dimensional, we have to consider at least 4 by 4 matrices. All right, does that make sense what I'm saying? All right, because we can't write down a complete set or a complete basis in terms of the 3 matrices because we need 4. Right? And so what we need to do is introduce a 4th. Right? And in order to do that, we have to move to a higher dimension for these matrices, and it has to be at least 4 by 4, right? Because it's even dimensional. We could consider, 962 dimensional operators, but let's start as simple as we can. Okay, so we'll start with 4 by 4 matrices. Right? And it turns out there's several different ways or different representations that you'll see for alpha and beta. And it's always a good thing if you're looking in other quantum books, or other, it's always like in the first couple pages, they'll give their conventions, right? They'll tell you what representation they use for these matrices. Okay, and that's always the first thing to look for if you're looking at a new book that you've never looked at before. All right, so know the representation that they're working in. So the most used representation is called the Weyl representation. And the nice thing about the Weyl representation is that you can write these guys in a block diagonal form. Right? So a block diagonal form means that this thing, alpha I, so you see that they depend on the Pauli matrices, but we know the Pauli matrices are 2 by 2. Right? So what this really is a 4 by 4 matrix. Right? But these zeros are 2 by 2 zero matrices, and these are the 2 by 2 Pauli matrices. So that's the nice thing about the Weyl representation. You can work in this block diagonal form, and you don't have to explicitly write down 4 by 4 matrices. Right? Okay. And then the beta matrix in this representation is diagonal, right? And the diagonals are made up of 2 by 2 identity matrices. Okay. All right, so that's all fine and good. So now we know how to write down the matrices, but now our matrices are 4 by 4, right? And so what that's telling us is that instead of our nice, 2-component spinner for the Dirac particle, we're going to have to expand that to four components, right, in order for the math to work out, right? Because we got 4 by 4, and that wouldn't work with a 2-component spinner. So we have to raise the dimensionality of our spinner to 4. Okay, but we know in nature, right? We knew in nature. What time is it? Okay, so we knew in nature, because I start seeing people gathering out there. So we know in nature that we only see 2 possible spin states, right? So this 4-component spinner would seem to say that there's 4 different spin states, but we know from from many experiments that there's only 2 spin states, right? So how do we interpret these extra spin states? Okay, and the answer is pretty easy to see once you consider the fact that the Hamiltonian, which is constructed out of alpha and beta, so that means the Hamiltonian has to also be traceless and even dimensional and all that other stuff, right? So if it's traceless and even dimensional, right? So this is the eigenvalue equation we're working with, right? And if alpha and beta are traceless, that means the Hamiltonian is traceless, and what that means is that the eigenvalues of the Hamiltonian have to sum up to be 0, right? So if you think about it, if you diagonalize the Hamiltonian, you would have your eigenvalues along the diagonal, right? And those eigenvalues, which are the EP, right? So you would need those things to sum up to be 0, right? And the way you do that is to say, okay, I have 4 eigenvalues, I have 2 positive ones, but I have these 2 negative ones, right? That's the only way that you can get this to work out, right? So these 2 positive states, we know how to interpret those. Those are the spin up, spin down electrons that we observe in nature. But what the hell are these negative energy states? Okay, and we'll come back to this later when we get more into the math. All right, so we've got a theory that's manifestly Lorentz invariant. That means it obeys special relativity. What we want to check now is if we're screwing up the conservation of probability, right? Like we did for the Klein-Gordon equation. So here we do basically the same thing. We take the Dirac equation, right? Multiply by the left by psi dagger, right? We take the Hermitian conjugate of the Dirac equation, multiply it by psi. So these are these 2 equations, and then I take the difference between these 2. Right? And what you see is when I take the difference, these mass terms are going to cancel out. But the time derivative terms and the spatial derivative terms are going to sum up. All right, so I end up with something that looks like this, okay, when I take the difference. And this has the right form, right? I can take this guy over to the other side. I can define the psi dagger psi to be rho, right? I can define the stuff in here, psi dagger alpha I psi, to be my current density, right? So I can write it in this nice compact form for a continuity equation, right? And so what you do is the normal thing. You take this thing you integrate it over all the space, right? And you use the Gauss's theorem, right, which tells us that del dot J vanishes, right? And we find that this current density, or this is like the probability, right, is conserved, right? Everybody see that? So this is the probability density, integrate over all the volume, that's the probability. D by dt of the probability is equal to 0. So the probability is conserved, okay? So that means that we can interpret rho, the way we define it, psi dagger psi, to be a positive definite probability density, which is exactly what we want in a quantum mechanical theory, okay? So that does it for today. Next time what we'll do is we want to make a connection with non-relativistic physics. So we want to take the Dirac equation and make sure it reproduces what we observe at, in the non-relativistic region. And then we'll start to talk about a more detailed discussion, so more math than we did today on special relativity and quantum mechanics. Okay? Okay, so I'll look at the calendar, figure out when the exam will be. It'll be last day of class, whenever that is. And I'll look at the homeworks and see what I got. Put something in the Dropbox for you for the weekend. Okay? All right. Have a good weekend.
Bye. Thank you.
The thing from last.
All right, see you, dummy.
Busy.
What's that?